Welcome to my YouTube channel. Myself Muthu Kumar, Assistant Professor, Konoda College of Engineering and Technology. So today I am going to deliver a lecture on instrumentation amplifier under the linear integrated circuits. So instrumentation amplifier, so it is a very important equipment for the industrial applications. So it is used to measure and control many physical quantities. For industry, so we need to measure the physical quantities like temperature, humidity, and flow. So we are using the instrumentation amplifier. So normally transducers are used to measure all these low voltage signals. So this low voltage can be amplified so as to drive the indicator or supply. So this is amplification can be done by instrumentation amplifier. Such an amplifier is an integral part of modern testing and measurement instrumentation. For industrial purpose, we need to measure many physical quantities like temperature, humidity, flow. For that purpose, so we are going for the instrumentation amplifier. So this instrumentation amplifier amplifies the transducer low output signal. Then amplified signal is given to the indicating devices. This instrumentation amplifier has the following characteristics or to need to meet the following requirements. The gain of the instrumentation amplifier is finite, accurate, and also stable one. Easy gain adjustment, high input and low output impedance. So it has high CMR or value. It consumes less power. Sleep rate is also high. Low thermal and time trips. Low DC offset voltage. So for the above characteristics, so APAM special APAM A725 satisfies all the requirements of the instrumentation amplifier. So another families are available: AD521, AD524, AD620, LM363 are some of the commercial and available chips. So these are the requirements of the or characteristics of the instrumentation amplifier. So this is the diagram of instrumentation amplifier. So it has two input stage, one is input stage, one is output stage. So input stage is made up of two non-inverting amplifiers. So a non-inverting amplifier, this is one, that is A1. So input V1 is given to the non-inverting terminal. So this is also one of the non-inverting amplifier. So input V2 is given to positive terminal. So these two non-inverting amplifiers forms the input stage. So the output stage is normally a differential amplifier. So output of A1 and A2 is given to the input for the A3. So finally we are getting the differential output. So this is the 3-APAM based circuit. Next we need to analyze this circuit. So instrumentation amplifier, so it's a basic difference amplifier at the output stage. So the output of A1 is V01, output of A2 is V02. So this difference voltage is given to the output stage of an amplifier. So finally we get this output voltage V0 is equal to R2 divided by R1 into V02 minus V01. So V01 minus V0 is the difference of input stage amplifiers. So this is a circuit diagram for two-stage amplifier, that is input stage. So input is V1, so that is given to the non-inverting terminal. So output is V01. This is RF1. This is the node G, node H, so RG, and RF2. So this is the of non-inverting, one of the non-inverting amplifier. So from this circuit, so we are going to calculate the current value. The next step. So from this diagram, So at node A, the potential is V1. So due to the virtual concept, so node B also has the same potential. So A and B has the same potential, that is V1. So also G has the same potential, but node A and node B. So we are going to write A is equal to VB is equal to VG is equal to V1. Similarly, for the APM A2, so we are giving the input V2. So considering C as a virtual ground, so D also has the same potential, C also has the same potential, also H also has the same potential. So we are going to write VC is equal to VD is equal to VH is equal to V2. So VA is equal to V1, VC, VD, VH is equal to V2. So from this circuit diagram, so we are going to calculate current I value between the node, so E and F. So here voltage is V01, here voltage is V02. So current equal to, that is I is equal to, so difference between the voltage V01 minus V02 divided by, so all the resistance connected between the E and F. So Rf1, Rg plus Rf. So current passing through the resistor Rf1, Rg, Rf2 is equal to I is equal to V01 minus V02 divided by Rf1 plus Rg plus Rf2. So from this equation, so we are going to calculate just, so V01 minus, so V02. Next step. So simplifying this equation number 4, so we get this formula. So we are going to consider Rf1 is equal to Rf2 is equal to, simply we are going to take Rf means, so equation number 4 modified as, so I is equal to V01 minus V02 divided by 2 Rf plus Rg. So Rf1 plus Rf2 is equal to 2 Rf. So on referring node G and H from the previous diagram, referring the node, so G and H, so referring the node G and H. So from this node, we are going to write the current equation. So I is equal to Vg minus Vh divided by Rg. So current passing through the resistance Rg is equal to Vg minus Vh divided by Rg. So this is equation number 6. So now equating equation number 5 and equation number 6. So V01 minus V02 divided by 2 Rf plus Rg is equal to, so this equation is equal to this equation, that is V1 minus V2 divided by Rg. So from this equation, we are going to calculate V01 minus V02 value. So V01 minus V02 is equal to, so Rf 2 Rf plus Rg into V2 minus V1 divided by Rg. So commonly taking, so Rg outside, so finally we get 1 plus 2 Rf divided by Rg into V2 minus V1. So V02 minus V01 is equal to this value. So equating, substituting the equation number 7 in equation number 1. So this is the value for V01 minus V02. So we are going to write in, so equation, so V0 is equal to R2 divided by R1 into, so 1 plus 2 Rf divided by Rg into V2 minus V1. So finally, so we are getting this equation. So this part is called gain of the amplifier. So 1 plus 2 Rf by, that is R2 into R2 divided by R1 into 1 plus 2 Rf divided by Rg is equal to, so gain of the instrumentation amplifier. So advantages. So with the variable resistance Rg, the gain can be controlled easily. So between the node G and H, the variable resistance Rg is available. If you vary this value, so you can control the gain value easily. The input impedance depends on the input impedance of the non-inverting amplifier. So input impedance depends upon the impedance of the non-inverting amplifier. The output impedance depends on the output impedance of A3, which is very low. So input impedance is high, output impedance is equal to very low. So CMRR value, that is common mode rejection ratio, is also very high. So it is the better stability and the gain. So finally, I'm going to conclude the topic with small recap. So for the industrial application, we need to measure and control any physical quantities like temperature, humidity, flow of the some molecules. So with this purpose, we are using the transducers. So to produce the low output voltage, this output voltage can be amplified with the help of instrumentation amplifier. Finally, the output will be displaced in the indicator. So it has the following characteristics. So this has the finite and accurate stable gain. Easy gain adjustment is possible. High input and low output impedance is available. High CMRR value consumes only less power. High sleeve rate, low thermal and time drift, low DC offset. So the special ICs are available. AD521, AD524, AD650, LM360 are the instrumentation amplifier based ICs. So this is a circuit diagram. So as input stage and output stage, the input stage is normal to non-inverting amplifiers. The output is given to the difference amplifier. So finally, we are getting the output V0 is equal to R2 by R1 into V01 minus V02. So this is the output voltage. So with the help of the node equations and the virtual current concept, so we are going to write the value for the potential at A and B, C equal to V1. Similarly, C, D, H, the potential is equal to V2. So I is equal to from the Ohm's law, I is equal to V01 minus V02 divided by RF1 plus RG plus RF2. So in this equation, so RF1 plus RF2 is equal to, that is RF1 is equal to RF2 is equal to, we are going to consider simply RF. So going to take this I value. So between the node G and H, so I is equal to Vg minus H divided by Rg. Similarly, Vg is equal to V1, already we derived V1 minus V2 divided by Rg. So substituting this I value in the equation number 6. So we get this equation. So from this equation, we are going to calculate V02 minus V01 value. So V02 minus V01 is equal to 2RF plus Rg into V2 minus V1 by Rg. So simplifying this equation, we get this type 1 plus 2RF divided by Rg, V2 minus V1. We are going to apply this V02 minus V01 in the equation number 1. That is R2 divided by R1 into V1 minus, that is V02 minus V1. So this is the final output value. So this part is called gain of the instrumentation amplifier. So advantages, so due to the value of variable resistance Rg, so gain can be easily controlled. Input impedance is equal to high, output impedance is equal to low. So CMR value is very high. So thank you for listening.